Okay, so we are going to continue where we left off on Friday in our discussion of the special theory of relativity. So when we had left off, we were talking about coordinate systems for the observer X, or for the observer O, and the observer O prime, where O primed is moving at a velocity v relative to O, and similarly, O is moving at a velocity negative v in the x direction relative to O primed. So the important one is the bottom one, measuring time uh, in O's coordinate system if the variables x primed and t primed are known. And so that's equal to gamma times, and then in parentheses, t primed plus v times x primed over c squared. And so there is a correction factor involved with uh, you know relating time in time coordinates in the old system to time coordinates in the new system, and that's assuming that t equals 0 overlaps in both cases. So we're going to differentiate that t with respect to t primed. And so you have the derivative of t with respect to t prime. So gamma doesn't change. The t prime becomes a 1. And you have v, and then you're taking the derivative of x primed with respect to t prime, and that's equal to u primed x. So that's the velocity of and here we're talking about a third object that's moving relative to both observer O and observer O primed. And so we're identifying that third object's coordinates. And also velocities. And so the derivative of x prime with respect to t prime is just the velocity of the third object that observer O primed uses. And what you'll see when we do these transformations is that you're going to need to identify observer O. You're going to need to identify observer O primed, and then you're going to need to identify which object is the third object, or which moving person or thing or observer is the third. And then you reverse this. So you have dt with respect to dt prime. So basically t is the time that it takes the third object to move from point A to point B relative to observer O. D primed is the time it takes the third object to move relative to observer O primed. We're going to flip that over, which is basically equivalent to inverting this. So we have 1 over this factor gamma times, in parentheses, 1 plus v u primed x divided by c squared. And that enables us to get values for the x, y, and z components of the third object's velocity with respect to observer O if we know those coordinates with respect to O primed and we know the velocity v. So ux is equal to dx over dt, which is equivalent to dx over d primed times dt over d prime. So again, using the derivations we did before, so using this derivation of x. So again, this is the position of the third object with respect to observer O, and x primed is the position of the third object with respect to observer O primed. And then y and y primed are the same, and z primed are the same, but the velocities aren't necessarily the same. So you have ux is equal to u primed x plus v divided by 1 plus vu primed x over c squared. So the gamma term factors out for ux. It does not factor out for uy and uz. You see, it's still in the denominator. And but you have u primed y and you have u primed z in the numerators in those cases. So you have this corrective factor involved. Okay, so let's see how these transformations work in real life. So let's start with problem number 19. An observer on Earth sees an alien vessel approach at a speed of 0.60 c, so 3/5 the speed of light. The Enterprise comes to the rescue, overtaking the aliens while moving directly towards Earth at a speed of 0.90 c relative to Earth. What is the relative speed of one vessel as seen by the other? So let's take a look at this. Let's set up the whiteboard. So we have the Earth. We have the alien vessel. And we have the Enterprise. And so one is moving at a speed of the alien vessel is moving at a speed of 0.60 c relative to the Earth. So we're going to make one of these v and one of these u prime. So we're going to put observer O on the Earth. And we are asked to find the relative speed of one vessel as seen by the other. And so maybe we're going to want the speed of one as seen by the other. So let's, again, the key to solving, we have observer O, we have observer O primed, and then we have the third object S that's moving relative to both. So we want to make, let's make the Enterprise observer S. And so this is observer O. The alien ship is observer O. And so this is O primed. So from our coordinate system, and again, we'll define right as positive and left as negative. So, so V in this case is equal to 0.6 c. U primed, which is the velocity of the Enterprise with respect to the Earth, is equal to negative 0.9 c. So again, the Earth is moving to the right, which we'll define as the positive x direction, relative to observer O, which we've defined as the alien vessel. And then the Enterprise is moving to the left at a velocity of 0.9 c relative to the Earth, but which we've defined as O prime. So what we want to do is find the velocity of the Enterprise relative to this observer. Now, if relativity weren't involved, the the Enterprise would be moving at a velocity of 0.3 c relative to observer O. That would be if relativity weren't involved, but let's see what happens when relativity is involved. So we want to find U. And so ux is equal to u primed x plus v. And so we'll call this u primed x. All the motion we'll say is in the x direction. And we're dividing that by 1 plus vu primed x divided by c squared. So let's see how that sets up. So u primed x, that's negative 0.9 c plus 0.6 c. So basically the numerator is the non-relativistic velocity. And then we have 1 plus v, which is 0.6 c. And multiply by u primed x. So keep the negative in. Divided by c squared. So on the top, we have negative 0.3 c. And on the denominator, we have 1 minus, and so this becomes 0.54. And so the c squared terms cancel out. So that's 0.54. And this should be 0.3 c, excuse me. So that's negative 0.3 divided by 0.46. So that becomes negative 0.65 c. So that's the speed at which this observer sees the Enterprise gaining on them. And so again, you're figuring out relative velocities. And again, you expect it to be negative because the Enterprise is moving to the left relative to the observer. So they're basically two things you need to keep in mind. One, you need to identify O primed, and then the third object, S. And so S is going to be the velocity of the object, or the object whose velocity you want to measure. O is going to be the object you're measuring the velocity, or the observer you're measuring the velocity relative to. And then the third object is O primed. And then you figure out V, and you figure out U primed X, and then you have enough information to figure out U. So keep that in mind. Make sure you identify O primed, and S correctly. And then the second thing is keep track of positives and negatives. They do matter. If an object is moving to the right relative to the object you're relative to the observer, then its velocity is positive. If it's moving to the left relative to the observer, then the velocity is negative. So it's important to keep track of pluses and minuses with this. So now we're going to move on to the second example. So suppose in figure 3611 that the origins of S and S primed overlap at T and T primed equals 0, and that S primed moves at a speed of V is equal to 30 meters per second in respect to S, with respect to S. In S prime, a person is resting at a point whose coordinates are X prime is equal to 25 meters, Y prime is equal to 20 meters, and Z prime is equal to 0. Calculate this person's coordinates in S, X, Y, Z at T equals 3.5 seconds and T equals 10.0 seconds. Use the Galilean transformation. So this one's not a relativistic problem. This is more of a relative position problem. So we're going to have S prime move to the right, and a person is resting in S prime, and you're relative to S prime. So the coordinates are X prime is equal to 25 meters, Y prime is equal to 20 meters, and Z prime is equal to 0. And we're assuming V moves to the right. So we're taking the positive X direction as the direction of the velocity. And in special relativity, velocity is constant, so we don't have to worry about the directions changing. So what do we have? So you have x is equal to x primed plus vt. In Galilean transformations, you're not worried about time. And, or, time doesn't change between one reference, in one frame of reference and another. And then y is equal to y primed, and z is equal to z primed. And so we are asked the person's coordinates at t equals 3.5 seconds, b is equal to, or t is equal to 10.0 seconds. So x primed is 25 meters and remains constant. Y prime, or in the relative to observer O prime, that's the case. Y primed is 20 meters. And Z primed is 0. So at t equals, and the first number is 3.5 and the second number is 10.0. So x is equal to 25 meters plus, and the velocity is equal to, v is equal to 30 meters per second. And so that's 3.5 seconds. So this number is, when you multiply it out, it's 105, but you only know it to two significant figures. And so that becomes basically 110 when you round up. And well, you have 105 and you have 25, and you only know it to three significant figures. So you can write it as 130 meters. Since you don't actually know it to the nearest unit, or the nearest one, you know it to the nearest 10, because there are only two significant figures in this term. I prefer to write it 1.3 times 10 to the 2 meters to signify that this 0 is insignificant. And it's insignificant because you only know these numbers to two significant figures. But when you multiply them together, it's a 3-digit number. All right, so now we go to t is equal to 10 seconds. So x is equal to 25 meters plus 30 meters per second times 10.0 seconds. Again, keep in mind, we only know the 30 to two significant figures. So this is 300. And so you add them together, you get 325. But again, you only know your answer to two significant figures because this is the two significant figures. So you could write that as 330 meters rounding up, or again, to the correct number of significant figures, the 3.3 times 10 to the 2 meters, again, so that it's understood that this 0 is not significant. So again, it's physics 4, but you still need to keep track of significant figures the right way. And so with that, that's the that's the transformations. And then y is just 20 meters and z is equal to 0. Those don't change throughout the process. Again, we're assuming v to be in the positive x direction unless specified otherwise. Okay, so let's go to another example. Repeat problem 20, which is the problem we just did, using the Lorentz transformation and a relative speed v is equal to 1.8 times 10 to the 8 meters per second. So now we are at or 1.80 times 10 to the 8 seconds. So now we are at, that's 6/10 the speed of light, or 60% the speed of light. And choosing the time to be 3.5 microseconds and 10.0 microseconds. So now we have to change a few things. Now V is equal to 1.80 times 10 to the 8 meters per second. And I'm going to write that as 0.600 C. So now let's go back and figure out the Lorentz transformation. So we're going to go back to this, and so we're going to assume that T primed is, so that these are T primed is equal to 3.5 microseconds and 10.0 microseconds. So we're going to assume that. And then everything else will fall into place. So going back to the first slide we showed today, y and z are still equal to y primed and z primed, but x is now equal to gamma times x plus vt. And times vt primed, excuse me. So again, y and z don't change. X, however, is equal to gamma times x primed plus v t primed. And so gamma, so that's basically equal to x primed plus v t primed over 1, or the square root of 1 minus v squared over c squared. So v squared over c squared is going to be 0.360 to 3 significant figures. Again, this number is just v squared over c squared. So you plug these in. Again, x primed is 25 meters. You have v and t. So you have the 25 meters plus and so that's 655. But again, and then you're dividing that or multiplying that by gamma, however. And so you get, when this is plugged in, when you plug everything in, and again, you only have 2 significant figures. So that's 8.2 times 10 to the 2 meters. And now over here, you have basically the same calculation. So it's 25 plus, but now you have 3 significant figures for both v and t primed. So that's So you get 1,825. But so your answer, you'll note, to three significant figures. And again, you're multiplying by gamma. And so it's three significant figures, but it's 4 digits. So you're going to write that as x is equal to 2.28 times 10 to the 3 meters. So in 10 microseconds, it's traveled over 2 kilometers. And again, gamma is just 1 divided by the square root of 1 minus 0.360. That becomes 1 divided by the square root of 0.64. That square root is simply 0.8. So gamma is 1 divided by 0.8, or 1.25. So you have that multiplying factor that comes into play in this. And so with that, so that's basically the same problem with the Lorentz transformations involved as the previous example. So now we're going to take it one step further. In problem 21, suppose that the person moves with a velocity whose components are u primed x equals u primed y equals 1.10 times 10 to the 8th meters per second. So now the person involved is no longer at rest. And so what will her velocity be with respect to s? So basically the original observer. So you want ux, uy, and if necessary, uz. So you're looking here. So u primed is z is 0. But you now have components for ux and uy. So let's figure out what those components are. So let's clear all this. So we know that u primed x is equal to 1.10 times 10 to the 8 meters per second. And u primed y is also equal to 1.10 times 10 to the 8 meters per second. And v, so the observer in reference, observer O primed, the primed reference system, is moving with still with a velocity of v is equal to 1.80. So we're going to keep the v is equal to 0.600 c. And it makes more sense to write it like that given the calculations. So u sub x. So this is how the person is moving relative to observer to observer the observer O primed. And now we're going to find the components of the velocity relative to observer O. And so ux is equal to u primed x plus v. And you're dividing that by 1 plus v u primed x divided by c squared. Okay, so, and this is equal to 1.80 times 10 to the 8 meters per second. So in the numerator, you have 2.90 times 10 to the 8 meters per second. And the denominator, that's 0.600 c. you can write this, the 1.1, as 0.367 C. So we'll do that because I think it'll make things a little bit easier. So that's 1 plus 0.600 times 0.367, and then the C terms cancel out in the denominator. And then plus 1. And so you get 2.38 times 10 to the 8th meters per second. So the moving person is not, moves more slowly relative to O than she does to O primed in this. And actually, no, excuse me, she moves more quickly relative to O primed. So she's 1.10, and it becomes 2.38. In a normal transformation, it would have been the numerator, 2.90 times 10 to the 8th meters per second. But what you get is 2.38 times 10 to the 8th meters per second. So, the relativistic effects make the relative velocity slower than it would be in a basic Galilean transformation. So uy is equal to u primed y, which we know, divided by gamma times 1 plus v u primed x over c squared. So gamma, again, you get from v, and so we already know that gamma, that's equal to 1 over the square root of 1 minus 0.600 squared. And so you do the math for that, that's equal to 1.25. So we'll put that in. So that's 1.25 times 1.10 times 10 to the 8 meters per second. And you're dividing by this term. So that's 1 plus, and again, what we have over here. Okay, and so when you do that, what you'll find is that you get only a slight change. So you get 1.13 times 10 to the 8 meters per second. So the movement is slightly different. The motion in the y direction is slightly different. It does get affected a little bit by the length contraction and the time dilation. More to the point, the time dilation. Okay, so and so one last example before we move on to momentum. So here we have two spaceships leave Earth in opposite directions. So let's get back to the lecture notes. Two spaceships leave Earth in opposite directions with a speed of 0.60 c with respect to Earth. What is the velocity of spaceship 1 relative to spaceship 2? What is the velocity of spaceship 2 relative to spaceship 1? Now, in non-relativistic terms, I mean, if we did the Galilean transformations, they'd be moving with the speed of 0.60, or rather, relative to each other, it'd be 1.20 c would be their speed relative to each other. In special relativity, we know it's not possible to exceed c. So let's see how this looks. So we have the Earth. We have Spaceship One. So Spaceship One going like this, and Spaceship Two going like that. And they both have a speed of 0.60 c relative to the Earth. And so we want to find the velocity of one relative to the other. So we'll call this observer O, and we'll call this observer S. So this is the velocity we want to find. And we want to find it relative to O. So the Earth is O primed. So we know that V, because observer O is moving to the left, then O primed is moving to the right. So V is equal to positive 0.60 Celsius. Again, keep track of your positives and negatives. So O primed is moving with a velocity of 0.60 c, to the right relative to observer O in this spaceship. And so we know that U primed is also 0.60 c, and they're both positive. And so we want to find U sub x, which is the velocity of this rocket ship, or this spaceship relative to this spaceship. So Ux is equal to, and then again, going back to the Lorentz transformation, Ux prime plus V divided by 1 plus VU primed x divided by c squared. So 1 So let's plug these in. Again, the numerator is what it would be in non-relativistic transformations, which would be 1.20 c. You add these two together. The denominator is 1 plus, so V is 0.60, and the denominator is 0.6, or the second number is 0.60. And so that's that becomes, and the c terms cancel out in the denominator, they cancel out. So you have 1.20 c, and 0.6 squared is 0.36. So you get 1.36 in the denominator. So you have 1.2 divided by 1.36. And so you get 0.882 times c. So object S is moving at 88% the speed of light relative to object O. So the rockets are basically moving at 88% of the speed of light relative to each other. And they're moving in opposite directions. So the velocity of S relative to observer O is 88% of the speed, or positive 88% the speed of light. The velocity of O with respect to S is negative 88% the speed of light. Again, defining positive to the right and negative to the left. And so that's basically how that works. So you figure out which thing you're measuring the velocity of, and that's going to be object S. What you're measuring its velocity relative to becomes observer O, and then observer O is moving, or rather, observer O primed is then moving a distance, or moving at a speed relative to O, and that speed is V. So again, you keep track of positives and negatives, what's moving to the right relative to what, and what's moving to the left relative to what. And you make sure that you define your observers in a way that makes it easy to solve the problem, and you keep those definitions consistent. So that's how that works. And that brings us to relativistic momentum. We're not going to go into a full rigorous definition of relativistic momentum, but uh, Einstein did a lot of thought experiments, and when he initially described relativity to people, or tried to describe relativity to people, he used these thought experiments so that they could understand, the mathematics, which was a bit more complicated. They can understand it conceptually. So ultimately, momentum in relativistic coordinates is equal to gamma times m times v. So we're going to set that up relatively, we're going to mirror one of Einstein's thought experiments here. So we have an observer O, throws a ball of mass m, and we'll call that ball A, of mass m in the positive y direction, with speed u, with subrelativistic speed u. And so this is a simplified version of the derivation. There's a more general derivation that's more complicated, but if you understand this, you can see how the more general derivation is going to go. Observer O primed moves with a relativistic velocity relativistic speed v in the positive x direction relative to O. She throws an identical ball B in the negative y direction. With the same speed u. So the balls collide elastically. So that they reverse direction but maintain their speed. maintain their speed in the thrower's reference frame. Now, here's the thing. Momentum is a conserved quantity, but it's a conserved quantity in all reference frames. And that applies at the relativistic level, or that applies at the subrelativistic level, but it also applies at the relativistic level. So you need to find, how you, what factor you would need to apply to the product of mass times velocity to make sure that momentum is conserved in every reference frame. So let's see how that works. So we'll start with ball A. And this is in observer O's reference frame. So its initial momentum in the x direction is 0. It's thrown up in the y direction. So from observer A's reference frame, it doesn't move in the x direction. And it's moving upward with a velocity u, at least before the collision. And object B is moving in the x direction with a velocity v. And in the y direction, now in its own reference frame, it's moving with a velocity it's moving with the velocity u, but due to length contraction, and that'd be negative u in its own velocity frame, or its own frame of reference, but due to length contraction, it's divided by gamma. So the velocity is divided by gamma. And so those are the components of the velocity. And because the masses are equal, they're not going to affect the momentum in this case. So this is the momentum before and the momentum, the momentum before the collision, or the components of the two objects. And again, to go from the velocity to the momentum, you just multiply everything by m. So what happens afterwards? Well, because it's a perfectly elastic collision with equal masses, the ball A just comes straight down. So it has no x component, but it has a y component of negative u. In the ball B, its x component remains v, but now its y component is positive u over gamma. So remember, the momentum should be conserved in all reference frames. So the x component of momentum is conserved. It's v, or times m, in the first, or in the x direction. In the y direction, you have u minus u over gamma initially, and you have u over gamma minus u finally. So the product of mass times velocity isn't conserved. But uh, remember, ball B is moving relativistic, relative to observer O. So uh, its movement is given by the value gamma, or it has a gamma value. So gamma times, if you multiply its vertical momentum by gamma, then, and remember, ball A is not moving with relativistic speed, so its value for gamma is simply 1. So uh, the product of gamma times the velocities is conserved, and so the product of uh, the sum of the velocities is not conserved, but the sum of gamma times the velocity is conserved. And so again, gamma doesn't break into components. So and its total velocity is essentially v, because this is relativistic and this term is not relativistic. So we're not its total velocity is not going to differ significantly from v. But you're still multiplying, or rather, you're still dividing the y component of its velocity by that factor gamma, because it is moving. And that's not so much length contraction, I guess that's time dilation that's causing that uh, that change in its velocity. And so again, the sum of the velocities, the total velocity vector, again, ignoring the masses because they're equal, the sums of the velocity is not conserved, but the sum of gamma times the velocity is conserved. And again, you can apply it more generally, where A could be moving, or where this could be relativistic as well. The mathematics gets more complicated, but Einstein's thought expression was basically, or thought experiment was basically to show that you can still conserve momentum in in all reference frames if you multiply the product of mass and velocity by the relativistic factor gamma. And so the same thing applies if you look from the O prime reference frame. I'll leave it to you to do that if you want. But basically, momentum is conserved in all reference frames. And again, whichever object is moving with the velocity v has its time dilated by the factor gamma. And so that lowers its speed in the y direction. But the product of gamma times m times v, the product of gamma times the object's mass times the velocity, and the total momentum using that definition is conserved in all reference frames. So again, going back to this basic version of this, Einstein used the thought experiment so that you can understand how momentum is conserved, without going into the fully rigorous derivation. That's quite a bit more involved, but you can see how this works. That relativistic momentum is equal to gamma times the mass times the velocity. Another consequence of that is that you can think of the mass as increasing by the factor of gamma as its velocity increases. And again, this is another way of saying that the mass can't exceed the speed of light, because as its velocity approaches v, its relativistic mass would increase proportionally. And the more to the point where you can't actually get to the speed of light, in that case. So let's now do an example. What is the momentum of a proton traveling at v is equal to 0.75 c? So we'll answer this in standard SI units, which would be kilogram meters per second squared. So it's a proton traveling at 3/4 the speed of light, or 0.75 times the speed of light. So P is equal to gamma mv. So first, let's figure out what gamma is. So gamma, and if you express the velocity as a fraction of the speed of light, it's actually easier to do this. So that's 1 divided by the square root of 1 minus 0.75 squared. And so putting that in, that gives 1.51. So that's the value of gamma. So about 1.5. So you have 1.51 times the mass of the object, which it's a proton. So that's 1.67 times 10 to the negative 27 kilograms. And the velocity is 0.75 times the speed of light. So we can write that as 0.75 times 3.00 times 10 to the 8 meters per second. And so, putting all this in, and we only have one significant, or two significant figures, that becomes 5.7 times 10 to the negative 19. And again, SI units for momentum, kilogram meters per second. So that's how you figure out the relativistic momentum in that case. Now, a particle travels at v is equal to 0.10 c. By what percentage will a calculation of its momentum be wrong if you include the classical formula and repeat for v is equal to 0.60 c? Okay, so let's start with v is equal to 0.10 c. So here, gamma is equal to 1 over 1 minus 0.01 squared, or 0.010 squared. And so that's 1 minus and so you get, for gammas, it's equal to 1.00. And don't forget the square root term. So okay, and okay. All right. And yeah, so basically 1.000. So the percentage is basically going to be negligible for the for part A. Certainly to two significant figures, it's not going to change at all. You can find out what it's going to be at um, I mean, you can find out what it's going to be, if you knew it to greater precision, but it's going to be a very, very tiny fraction. And however, for the second one, that's again, wait a second. I did something not quite right. Um, my apologies. It's not 1%, it's 10%. So the square of that is 0.01. So that's 1.0050 up here. So basically, the answer is going to be changed by 0.5% when you're 1%, or rather 1/10 the speed of light. When you are what was it again? 0.60. Right, 0.60 C. So when you have 0.06 or 0.60 C, again, we already did this. That becomes 1.25. The denominator becomes 0.8. And so you invert that. That becomes 1.25. And that's with the square root included. So for that, now you're talking a 25% error. And uh, so the actual answer is 1.25 times what you would get if you just use classical momentum. So you basically got a 25% error. And here, for 1/10 the speed of light, it's about 5/10 of 1%. And you can figure out things more precisely than that, but you can see that approximately. So the percent error is equal to the absolute value of P calculated, and again, this is calculated without assuming relativity, times P actual divided by P actual times 100%. And so the calculated value, so we know that that's MV minus 1.0050 MV divided by 1.0050 MV times 100%. So the MV terms don't matter, MV being the non-relativistic version. And so you do that, you get, again, with the absolute value signs, you get 1.00, basically 50. So it doesn't change significantly it doesn't differ significantly from gamma. So the percent error is that's a 0. So the percent error in the first one is 0.0050 or 0.50%. So it's about 0.5%. For the second one, the percent error is equal to 0.25 MV divided by 1.25 MV. And so you get from that, doing the math, about a 20% error. So when you're traveling at 6/10 the speed of light, you'll get a 60% or rather a 20% error, excuse me, between your measurement, your calculation calculation of the momentum without using relativity and what the correct value for the momentum is. So there's a 20% error. And for 1% the speed of light, it's half, or rather 1/10 the speed of light, the error is 0.5%. So now we've gone from relativistic momentum to relativistic energy. And Einstein did another thought experiment. This one involved a box and a that emits a photon on one side and then reabsorbs it on the other side. So the photon has momentum, which means the box is going to move. And then it absorbs it on the other side, at which point the box has stopped moving. So the box shifts a little bit, in this thought experiment. But the center of mass should not shift in this, because ultimately the mass hasn't changed. So what Einstein was did in his thought experiment was, well, what equivalent mass would the photon of energy E have to be in order for in order for the center of mass to remain what it was initially. And so it requires knowing the momentum of the photon, which is the subject of the next chapter. So I'm not going to go through this derivation in full detail, but what he found out was that if the equivalent, if the photon had an equivalent mass equal to its energy divided by c squared, then the center of mass of the system would not actually change. And so Einstein hypothesized that when you're transporting energy, it's equivalent to transporting mass, that mass and energy somehow have this equivalence that's related to c squared. So with that in mind, does the mc squared term show up in your other definitions? Someplace else in the relativistic calculations. So you can use the formula for relativistic momentum to calculate relativistic kinetic energy. And here's how you do that. So from the work energy theorem, the kinetic energy, or the change in kinetic energy, is equal to the work done, which is equal to f dot dx with an integral. And if the object is moving relativistically in the x direction, you can write the force as the change in momentum with respect to time times dx. And dx over dt is just the velocity. So you can write this as v dp. Well, okay. So that gives you an integral that you can work with. And you can also write that as v times the differential of gamma mv. So we're going to need to evaluate this differential here. We need to figure out what the d of gamma mv is. Now, gamma depends on the velocity. So you're going to get something, some function of the velocity times dv with the percentage involved. And the mass we can bring out. So that this becomes d times gamma v. So that it looks like that. And so that becomes, from the product rule, v d gamma plus gamma dv. So we need to solve for this. So the first thing we need to do is figure out, well, what's d gamma? So gamma is equal to 1 minus v squared over c squared to the negative 1/2. So d gamma is equal to negative 1/2 times 1 minus v squared over c squared to the negative 3/2, multiplied by the derivative inside here, which is negative 2v over c squared. Okay, so, and then don't forget the dv term. So you can write this, the negatives cancel out and the 2 and the 1/2 cancel out. So you can write this as v dv over c squared times 1 minus v squared over c squared to the negative 3/2 power. So that's d gamma. So now we can write d times gamma v as being equal to, so we have v d gamma, so that becomes v squared dv over c squared times 1 minus v squared over c squared to the negative 3/2 plus dv times 1 minus v squared over c squared to the negative 1/2. So, so taking this further, and so, yeah, you can write this as v squared dv over c squared, 1 minus v squared over c squared to the negative 3/2 plus dv 1 minus v squared over c squared times 1 minus v squared over c squared to the negative 3/2. So doing a little bit of creative algebra. Basically, multiplying it by 1 minus v squared over c squared and then dividing by 1 minus v squared over c squared. So now you have the negative 3/2 term in common, and you have dv common. And so when you factor them together, you get v squared over c squared plus 1 minus v squared over c squared. So what that leaves you with is just the 1. So you have dv dv times 1 minus v squared over c squared to the negative 3/2. All right, so that's your differential. And so delta K is equal to M, and then you have a V term in here too. So you have VdV, and you're going from your initial kinetic energy, a rest kinetic energy, so starting from rest and going to a final velocity V. So that's VdV over, well, actually, we won't write that. We'll write it like this. VdV, and again, you have V times this differential, so you don't forget the V term. And but that stays in the integral, whereas the M you can bring out. So you have V dV multiplied by 1 minus V squared over C squared to the negative 3/2. And this is actually a very doable integral. So we'll make some space for ourselves over here. But this integral is very easy to do with a substitution. What you're doing is, so we'll let U, we'll call it capital U, equal 1 minus V squared over C squared, so that du is equal to negative 2V dV over C squared. So that V dV is equal to C squared, or negative C squared d capital U over 2. Okay, so now let's plug that in. So the M stays over here. Instead of going from 0, you're starting at 1. And then V just becomes 1 minus V squared over C squared. And so now you have the VdV is equal to negative C squared over 2 du. And you're multiplying by this. So this is now U to the negative 3/2. So plugging that in, you get negative M C squared over 2. And you have 1, and again, 1 minus V squared over C squared. The U to the negative 3/2, when you integrate that, that becomes, well, that's U to the negative 3/2 du. So now when you integrate that, you still have the negative MC squared over 2. This becomes U to the negative 1/2 over negative 1/2. And notice you get a few things canceling out conveniently. And you get 1 and 1 minus V squared over C squared at the top. So you get, the 2's and the 1/2 and the negatives drop out. So you get MC squared. And then you have 1 over the square root. This becomes 1 over the square root of this, which is just gamma. 1 over the square root of this term is just gamma, and then you're subtracting from that 1. So the kinetic energy then becomes gamma MC squared minus MC squared. So you still have that mc squared term coming in. So Einstein sort of made the leap of faith, which subsequently has been borne out by experiment many, many, many times over, that objects have a rest energy equal to mc squared, and that their total energy is gamma mc squared. And then, the rest energy is just the mc squared term. So basically, mass is equal to stored energy. So again, this came out a combination of thought experiments and um, some mathematical derivations. So we came up with total energy as being equal to gamma mc squared. Kinetic energy is equal to gamma minus 1 mc squared. And so, and if you do a power series expansion of this, of gamma minus 1, your first order would be 1, which would get subtracted out. Your second order would be 1/2 v squared over c squared. And when you multiply that by mc squared, you get 1/2 mv squared. So basically, a first order power law expansion of the relativistic kinetic energy gives you 1/2 mv squared. And then you can, what if instead of relating it to um, um, ener- um, uh, velocity, you want to relate it to momentum. So how does that work? So P is equal to gamma times mv. Now what we're going to want to do is instead of solving for P in terms of velocity, we're going to solve for velocity in terms of momentum. And with this, and outside of this gamma term. So we have P is equal to mv over the square root of 1 minus v squared over c squared. So we're going to solve for v in terms of P. P squared is equal to m squared v squared over 1 minus v squared over c squared. And so we're going to flip the p squared in this term. So we get 1 minus v squared over c squared is equal to m squared v squared over p squared. Multiplying c squared by both sides, on both sides you get c squared minus v squared is equal to m squared v squared c squared over p squared. So bringing this up, you get v squared multiplied by m squared c squared over p squared minus 1 is equal to c squared. And so that gives you your opportunity to solve this for v. So v is equal to c squared. And all right, let's see. So okay, so that's m squared c squared over p squared minus 1. And so we'll multiply everything by p. And so we get p squared c squared. So you multiply the numerator by p squared, and then you have m squared c squared minus p squared in the denominator. And so that's how you relate v to p. So how does that affect you're solving for relativistic energy in terms of momentum? So your total energy is equal to gamma mc squared. So let's set that up. Now that we've solved for v in terms of p, we can solve for the energy in terms of p. So we have E is equal to gamma mc squared. So this is the total energy, gamma mc squared. We can write E squared is equal to gamma squared m squared c to the fourth. So that becomes m squared c to the fourth over 1 minus v squared over c squared. But now we can plug this terms in. So we have m squared c to the fourth. And so this becomes, so we have 1 minus v squared, which we have, and then that's over c squared. So that becomes 1 minus p squared over m squared c squared minus p squared. So what we then do is multiply the numerator and the denominator, but by what we have in the fraction. And so that's m squared c squared minus p squared. And you're dividing by, so this becomes m squared c squared minus p squared minus p squared. Well, hold on. There should be a plus term in here. Okay, so let's get back to that, for a second. So, so you have P is equal to gamma mv. P squared is equal to gamma squared m squared v squared is equal to m squared v squared over 1 minus v squared over c squared. Like that. And so that becomes p squared minus, right, p squared minus v squared p squared over c squared is equal to m squared v squared. And so v squared, yeah, so there is a plus. Okay. V squared, that's m squared plus p squared over c squared. And that's equal to p squared. And so that v squared then is equal to p squared over m squared plus p squared over c squared. and you multiply the numerators and the denominators, you get p squared c squared over m squared c squared plus p squared. Okay. Okay, so there's a plus here. Now it makes sense. And so you plug that in. So that becomes that. And so you have mc squared c squared plus p squared, and then you have on the denominator m squared c squared plus p squared minus p squared. So that just becomes m squared c squared. So those terms cancel out, and you're just left with the c squared in the denominator, or in the numerator. And so what you're left with for the total energy, you get p squared c squared plus m squared times c to the fourth. And so again, going back to the terminology. So expressing energy in terms of momentum, it's the square root of p squared c squared plus m squared c to the fourth. So again, if the momentum is 0, you wind up with E is equal to mc squared. So you have this total energy has a mc squared term in it corresponding to the rest mass. So what we'll do is we'll finish with a couple of examples. So calculate the rest energy of an electron in joules and in mega electron volts. So 1 electron volt is 1.60 times 10 to the 19 joules. A mega electron volt is 1.60 times 10 to the negative 13 joules. So let's start with this in terms of joules. So we'll use the units we know. What you'll see as you move on is that it's often easier in modern physics to work with electron volts or mega electron volts than it is to work with joules. So that's 1.67 times 10 to the negative 27 kilograms. And then you're multiplying by C. So 3.00 times 10 to the 8 meters per second. And you're squaring that. And so in joules, that is that's 1.50 times 10 to the negative 10 joules. In mega electron volts, you're dividing that by 1.6 times 10 to the negative 13, because that's the mega electron volts in a joule, and you get 939 mega electron volts. So that's the rest energy in mega electron volts of a proton. So let's go on to another example. When a uranium nucleus at rest breaks apart in the process known as fission in a nuclear reactor, the resulting fragments have a total kinetic energy of about 200 mega electron volts. So how much mass was lost in the process? So 200 mega electron volts of mass was converted into kinetic energy. And so you want to convert the 200 mega electron volts into energy, or rather from energy to mass. So again, E is equal to mc squared. So M is equal to the energy divided by c squared. So the energy is 200 mega electron volts. And you multiply that by 1.60 times 10 to the negative 13 to get joules per mega electron volt. And again, you're dividing by c squared. So that's 3.00 times 10 to the negative 8 meters per second. Or rather 10 to the 8, excuse me. All right, and so you plug those numbers in. And you get 3.55 or 3.56 times 10 to the negative 28 kilograms. So about a quarter the mass of one proton. But keep in mind, uranium has many protons and many neutrons in it. So let's go to a third example. The total annual energy consumption in the United States is about 8 times 10 to the 19 joules. How much mass would have to be converted to energy to fuel this need? So if it were all done through some sort of nuclear process, how much mass would you need to shed? And so, again, E is equal to mc squared. The fact that nuclear energy exists is more than enough proof that Einstein was onto something by saying that mass was stored energy. So again, the mass is equal to E over c squared. So the energy is 8.8 times 10 to the 19 joules. And you're dividing that by 3 squared, or by c squared. So that's 3 times 10 to the 8th, and you're squaring it. And so that gives to 9 times 10 to the 2 kilograms. So 900 kilograms it would take. Not necessarily that big of a number. And it's basically the mass of about 6 people. And, if you converted all of that to energy, that mass to energy, you could fuel the United States for a year. And then that brings us to the last problem. And it's the last thing we're going to do today. Calculate the mass of a proton in mega electron volts per c squared. Well, that's just the rest energy of the electron in mega electron volts. So sometimes you'll see the mass expressed not in kilograms, but in mega electron volts over c squared. So what exactly does that mean? So getting back to the whiteboard, you see the mass is equal to the energy divided by c squared. So what you do is you figure out the energy in mega electron volts and divide that by c squared. So what you have is the energy. And so we did that right up here. So that's 1.67 times 10 to the negative 27 kilograms times c squared, and that gives you joules. You convert that to mega electron volts. So you can equivalently say that the rest mass of a proton is equal to 939 mega electron volts over c squared. So that this term and so 1.67 times 10 to the negative 27 kilograms is equal to 939 mega electron volts over c squared. So basically, you take the mass in kilograms, you multiply that by c squared to get joules, you divide by 1.60 times 10 to the negative 13 to go from joules to mega electron volts. And then, so that's the energy in terms of mega electron volts, but you can also write the mass as 939 mega electron volts divided by c squared. And so sometimes you'll see it written this way. Okay, so that's all we're going to talk about today. That is the chapter on special relativity. So Friday, we will go over problems for special relativity. And, then, hopefully we can meet in person and do do an experiment where we're measuring the speed of light. And so if you have any questions, you can reach me by email or come to the office hours.